Welcome to This Explainer. Today, we're popping the hood on nature's ultimate biological engine. We're going to explore a true marvel of evolutionary engineering to figure out exactly how the avian cardiovascular system is built for the absolute extreme. I'm talking about surviving zero oxygen depths, soaring right over Mount Everest, and powering the single most energetically demanding form of locomotion on the planet, flapping flight. To put this kind of power into perspective, picture an engine revving so fast that its moving parts are literally just a blur. Well, that's exactly what the heart of a giant hummingbird does when it's in flight. It hits a massive 1,020 beats per minute. Now, for us humans, a maximum heart rate during extreme exercise might briefly brush the 200 mark, right? But this avian heart, it operates on a completely different physiological plane. So that brings us to the million-dollar question. How on earth does a biological pump survive that kind of stress without just exploding? To answer how this living engine sustains such extreme physical stress without failing, we need to compare its anatomical blueprint directly to our own. Section 1. Built for the extreme. Okay, let's look at the math here. Birds and mammals separated on the evolutionary tree over 200 million years ago, and these scaling equations basically prove that birds are just built differently. If you look at it, for any given body size, a bird has a significantly heavier heart than a mammal of the exact same weight. This extra cardiac mass is absolutely crucial. It's a foundational requirement to sustain flight. It's quite literally a bigger engine squeezed into a lightweight chassis. Because of this unique mathematical scaling, birds possess a massive cardiovascular advantage over us. They can push much larger stroke volumes, meaning they're pumping way more blood with every single beat. Because of this, larger birds have lower resting heart rates, but still manage to maintain a proportionately higher overall cardiac output than mammals of the exact same body mass. Long story short, they move more fuel and more oxygen far more efficiently. Section 2. Anatomy of the avian heart. Now, having a massive pump is great, but if you can't supply that pump with energy, the whole system just collapses. Birds solve this problem with an incredibly extensive coronary circulation system. You can see the dense network of both superficial and deep branches of the coronary arteries. These act as high-capacity fuel lines for that continuously pumping heart muscle. Without this super intricate, high-flow plumbing, the engine would stall out completely. Get this, the crucial takeaway here is staggering. Exactly 8% of the bird's entire cardiac output goes strictly to feeding the heart muscle itself. To put that into context, this constantly active cardiac muscle needs a significantly higher blood flow rate than resting skeletal muscle. The avian heart is so immensely powerful that it practically demands a greedy share of its own output just to keep running. Section 3. Upside-down electrical system. Now, to keep this powerhouse pump in perfect rhythm, it relies on some highly precise electrical wiring. Let's do a quick definition here. An electrocardiogram, or ECG, measures the summed electrical activity of the heart. By mapping the physical direction of this signal, which is known as the Einthoven vector, we track the wave as the heart muscle contracts. In humans, this wave travels in a way that typically produces a nice positive spike on a monitor. But in birds, this wiring is a fascinating evolutionary quirk. When you measure the main ventricular contraction wave in a bird through their Purkinje system, it actually has a negative polarity. Why? Because the bird's electrical vector points almost straight down their body axis. Their electrical system is essentially upside down compared to ours, firing powerfully from the top down to squeeze the blood up and out. So with this downward-pointing electrical axis, and knowing that birds don't have exceptionally high blood pressure compared to us mammals, you might be wondering, wait, how does blood successfully flow all the way up the incredibly long necks of birds like ostriches or emus? Gravity seems like it would be an insurmountable hurdle, right? Well, the answer is incredibly elegant. The circulatory system actually acts just like a siphon loop. The gravitational pressure of the descending venous blood coming down from the head perfectly counterbalances the gravity of the ascending arterial blood going up. Because it's a beautifully closed loop, pulling that blood uphill is completely effortless. It's just fluid dynamics working flawlessly in nature's favor. Section 4. Navigating extreme environments. Of course, birds aren't just flying around in perfect sea-level conditions. They push this biological engine to the absolute limits of the biosphere. Take the bar-headed goose. This bird achieves the unthinkable, taking on annual migrations over mountain ranges at altitudes up to 7,250 meters. Up there, they are flying in an environment with just 7% oxygen. They manage to survive thanks to hypertrophied or enlarged hearts and these incredibly dense capillary networks that literally squeeze every last drop of oxygen into their tissues when the air is perilously thin. Then, if we jump to the complete opposite physical extreme, we have deep diving birds like emperor penguins. They push their physiology right to the absolute edge of what researchers call the aerobic dive limit. This is the maximum duration a bird can hold its breath underwater before its muscles run out of oxygen and start producing toxic rising levels of blood lactate. To survive these wildly different environments, the avian cardiovascular system exhibits completely opposing extreme reactions. Taking flight triggers explosive tachycardia, which is an instant, massive acceleration of the heart rate. But on the flip side, deep water submersion triggers extreme bradycardia. The heart severely slows down, sometimes dropping way below resting levels, all while somehow magically maintaining its stroke volume to aggressively conserve oxygen in the dark depths.
Section 5. Nature's ultimate biological pump.
From surviving zero oxygen aquatic depths to soaring miles high, this kind of adaptability isn't just something they learn, it's hardwired from the very beginning. If you look closely at the intricate embryonic circulation of a bird, you'll see the precise autonomic regulation developing perfectly while the bird is still just a tiny embryo sitting inside the shell. It's establishing the exact adrenergic and cholinergic tones that will one day dictate those extreme heart rate shifts during a deep dive or a high flight. And because of this deep, specialized foundation, even the most common bird possesses what look like superhuman capabilities. Take an ordinary pigeon taking off from a park bench, an animal we literally see every day. It can instantaneously increase its oxygen consumption by an astounding 10 to 17-fold. Its heart rate rockets from around 110 beats per minute to over 660, perfectly meeting the immense metabolic demands of flight in a fraction of a second. All of this leaves us with one incredibly exciting question about the future. If nature engineered an engine this powerful, this efficient, and this adaptable millions of years ago, what current limitations in human technology could we overcome by mimicking avian physiology? As we look to build better pumps, better fluid systems, and more efficient aerodynamic engines, the ultimate blueprints might just be flying right above our heads. Thanks so much for joining me for this explainer, and I really hope you leave today with a new